Okay guys, in this video we're going to talk about phase changes and kind of how we can graphically represent the phase changing through the entire heating curve. So we're going to start with a little video for you guys.
When heat is applied to a solid, its temperature and vapor pressure increase with increasing temperature because the molecules of the solid have increasing kinetic energy. At the melting temperature, heat is absorbed as the solid is converted to liquid at a constant temperature. When melting is complete, the temperature of the liquid and its vapor pressure increase. At the boiling point, temperature remains constant as heat is absorbed to convert the liquid to the gas phase. When all the molecules are in the gas phase, the temperature again increases as the gas phase molecules acquire additional kinetic energy. On this graph of time versus temperature, the first segment represents heating of the solid. At point A, the solid melts. The temperature remains constant while melting occurs. At B, all the solid has melted, and the temperature again increases as the liquid is heated. At C, the liquid boils. Again, temperature remains constant with time until all the liquid has been converted to gas at point D. Then temperature again increases as the gas is heated.
Okay, so we see the kind of the basic heating curve that we also can see when we do our lab with the snow and heating that kind of stuff up. We're going to jump over to a website that also kind of shows this now. So we see here, I've kind of done a few different heating curves, and what I'm going to do is I'm going to reset this graph, and we're going to kind of run this. So we're going to start by setting this at like 200 watts. Okay, so 200 watts is basically the energy input or the power that's being put into this thing to heat it. And if I start to heat it now, we start to see that originally our graph will go up, and then it's going to flatline. Okay, and it's going to flatline for a while because it takes some time for that melting process to occur. And then now we're in our liquid phase, and now we're heating up as a liquid. And then again, it's going to flatline. And now we're doing the process of boiling. And we can see here that it takes a lot longer to boil this. Okay, so using the same amount of power, it takes us much longer to boil this substance than it did to actually melt it. Which means if it takes longer to boil something, okay, same amount of energy input, it took longer to happen, it probably takes more energy total to get something to boil. Okay, so as you take a look at that, typically speaking, substances take much more time to boil than they do to melt, which means it takes more energy for them to happen. Okay, now if I run this experiment again, and let's say we're going to double our power, and we're going to reset the experiment, and now I heat this, you'll notice that with double the power, okay, we're getting things that happen much faster. Okay, we get a much steeper slope here. Okay, almost double the slope. The time it takes to melt is cut in half. The time it's going to take to boil is going to be cut in half. Those kind of things happen because the speed at which this happens is going to be directly related to the actual energy that you put in to make it happen. Okay, and obviously if we cut this thing down to half of what our original and then heat this up, we'll see that we have this much slower process as we go through, and things should take twice as long now. Okay, so in terms of how long these things take, kind of what the slopes kind of look like, it is a relationship with the amount of energy you put in to make these things happen. Okay, all right, we're not going to keep heating this thing up because it's going to take us forever. You're going to basically see the same ideas you've seen before. So we're going to jump back now to our little show, and we're going to talk about the actual curve. So this is an example of data that we would have gotten from heating up water, and things that we want to make note of. Okay, a lot of times students miss the solid phase. So before you hit that flat line, you actually do have a little solid phase that's going on. You need to warm that up. Okay, and then when you flatline, that's your melting freezing. Now notice they say melting and freezing because if you're warming this up, it's melting. But if you're cooling it down, it's freezing. So your melting point and your freezing point are actually the exact same thing, just the opposite direction. Okay. Then you have your liquid phase as you warm up your liquid. And then you have your boiling and condensing phase. So boiling, of course, would be if you're warming it up. Condensing would be if you were cooling it down. And then finally, you have your gas phase over here. Okay. Now, one thing to note, we have these little spots here that really aren't identified, and they're transitional places. Okay. In an ideal world, this would come up, make a sharp right-hand corner, and it would go right from liquid to boiling. In the real world, however, you can't get an even mix of your sample perfectly. Okay. Even with mechanical stirrers and magnetic stirring devices, you can't get it to be perfect. Also, if you're putting more energy in than the system can kind of handle, you always create some sort of like ramp in and ramp out of these different steps or these phases. So that's very common to see these little curve ins and curves out here. It's not ideal like you would see like a computer generated kind of deal. Okay, so we've already kind of answered this. What takes more energy, boil to melt? So we know that's actually to boil. And then what happens to the temperature during a phase change? Well, if we look, we have pretty much a flat line here, and we have pretty much a flat line here. So during a temperature change, or sorry, during a phase change, there's no change in temperature. So if there's no change in temperature, we're really not changing the average kinetic energy during that point. So the kinetic energy is staying the same. What we're doing is we're breaking those intermolecular forces, and that's what's using up all that energy, is to break those bonds. So we're changing some potential energy in there, but the kinetic energy is actually staying the same. Okay? So that's phase change stuff, guys. That's it. Thank you.